VLSos here. This is a video lesson on graphing x equals y squared. We're going to start with something very different, y equals x squared. What we're starting with is familiar to us. Again, like many times in the past, this is the graph of the parent parabola. This equation is parent quadratic, the simplest form of quadratic there is, and it has this hopefully very familiar curve. But what do we do to graph x is equal to y squared? Notice that the variables got switched, and in doing so we've created something very different. Well, we could begin our graph by a table where we choose some x and then use the equation to find y. What if we chose 4 to be x? What's the corresponding value of y? Well, we're asking 4 is equal to what squared? What do we square to get 4? 2. But we might catch ourselves and think there's something else that we could square to get positive 4. If y was negative 2, we would square it and get positive 4. So we're putting the same value in for x and getting two different y values. That's a problem. I'm going to graph these points. If I put 4 into this function here, or equation, then I could get a y value of positive 2 and also a y value of negative 2, because both 2 and negative 2 squared is equal to positive 4. This isn't a function. The equation x is equal to y squared is not a function because we have two different y values for the same input or domain value. Well, how would we arrive at that conclusion algebraically? Or what would I do with this? How could I deal with this if I was working with this mathematically instead of investigating points? If I have the expression x is equal to y squared, I might want to solve for y, because I'm used to that, to make graphing a little more easy. How do I solve for y in this case? I'm going to undo the square with the inverse square root. When I do, I get the square root of x is equal to, well, the square and the square root cancel out. So I'm getting an equation which is a function. It's the parent square root function. But wait a minute, I might catch myself. It's not just the square root of x on the other side. I have to consider that this side can be both positive and negative. Again, squaring kind of cancels out a negative. Squaring something, if it's positive, keeps it positive, and if it's negative, it makes it positive. So squaring you can think of as an operation that cancels out the negative. So if we're going to undo that, then we have to account for the fact that we are recreating both the positive and negative versions. The square cancels it out. The square root reintroduces positive and negative. And this here is two distinct functions together in one expression. This, y is equal to the plus and minus the square root of x, can be thought of as the equation y is equal to the square root of x and the distinct separate equation y is equal to the negative square root of x. And together, they are the relation that we started with, x is equal to the square of y. So I can graph these two functions separately. When I do, I get the parent square root curve and a reflection of the parent square root curve across the x-axis. In this equation here, we're reflecting across the x-axis. Even though we have moved the negative over to this side in order to get y by itself, this negative is grouped with the y variable because it's not under the radical sign with the x, it's affecting y. And we know that when we make y negative, it's an x-axis reflection. The x-axis reflection of the parent square root looks like this. This here is the graph of two distinct functions, these two, and it is not a parabola. Though it retains the same kind of curve and is the same shape as a parabola, we do not call it a parabola because it's not the graph of a single function. It's two square root curves. One is the parent square root and the other is a transformation of it.